Okay, all right, so it's 7 o'clock, we'll go ahead and get started. Like I said, today we're covering sections 5.1, 5.2, and 5.3. So 5.1 is all about the inverse functions. Basically our whole last chapter was all about functions and domain and range and all of that fun stuff. So 5, we're just going to be specifically talking about the inverse of a function. So again, a function is a relation where no elements of the domain repeat. An inverse relation, because it doesn't necessarily have to be a function, an inverse relation simply swaps your input and your output. So again, it literally inverts them. So the inverse becomes the output becomes the input. So the easiest way to express this is if we have a simple function where they give inputs and outputs. Remember, they typically would list them as x's and y's. So your x is your input value, your y is your output value. So this has an input of 1, output of 2, input of 3, output of 4, input of 5, output of 6. Okay, remember your x's are your ins, your y's are your outs.
Math class.
Okay, so if this is your initial function, the notation for inverse, we'll put a -1 up here. It looks like an exponent, but it's not. This basically just means the inverse function. So when you see that -1 up there, that's referring to the inverse function. And the inverse function, again, is just going to swap your x and your y. So instead of 1, 2, the inverse is going to be 2, 1. Okay, same thing. Instead of 3, 4, it's going to swap to 4, 3. And then instead of 5, 6, it's going to swap that to 6, 5. So literally the inverse function just swaps your x and your y's.
The login address is Zoom.
.otc.us, I think. Yeah. Okay. So anyway, the inverse function literally takes your x's and your y's and just swaps them. This is the easiest way to express it because this shows inputs and outputs. Okay, we'll be doing a couple of different things where we're actually finding the inverse of a function given an actual function like an equation. Okay, so to find the function, to find that inverse, okay, first we have to determine if the function is 1-to-1. Okay, we talked about this in the last unit, but if a function is 1-to-1, then it can have an inverse. If it is not 1-to-1, then it's technically said to be invertible. It does not have an inverse. Okay, so remember to see if it's 1-to-1, if you're looking at it as from an equation perspective, you want no even exponents of x. So again, that's no even exponents of x. So for example, f of x equals x to the third. All right, somebody enter. All right. Got it. Okay. So again, f of x equals x to the third. This is 1-to-1. So we could find the inverse, and I'll talk about how to find the inverse here in just a second. But just saying that it is 1-to-1 means we can find the inverse. And same thing, if I said x to the third plus 1, okay, or x to the third plus 1x. These are all 1-to-1, and you can therefore find the inverse. However, anything with an even exponent, like an x squared or an x to the fourth, okay, is not 1-to-1 and therefore has no inverse. So again, in order to find the inverse, we first have to see if it's 1-to-1. If the function is 1-to-1, then we can go through the steps of finding the inverse. So odd exponents are fine. Even numbers are fine, just not even exponents. Having an x squared or an x to the fourth anywhere within the problem means it's not 1-to-1, and therefore there will be no inverse. As long as your exponents are odd or not there, okay, then it is 1-to-1 and we can find the inverse. To find the inverse, okay, basically we're going to rewrite f of x as y. Then we're going to switch our x and our y. And then we want to solve for y, meaning we want to get the y by itself. Okay, I muted everybody. If you have a question, you're going to need to unmute to ask it. Just we were getting a lot of background noise. So I just muted everybody. So if you have a question, just unmute and then you can ask your question. Okay, anyway, so far, again, we just replaced f of x with y. Then we swapped our x and our y's. And now we got to get y by itself. So typical equation solving, if I subtract 1 from both sides, divide everything by 3, then this is my inverse function, this x minus 1 over 3. So the way we would write that is f to the negative 1 x, and then we would write that inverse function. So again, kind of step by step. Simply replace f of x with a y. Then we swapped our x and our y's. Then we basically want to get y by itself. So we subtracted 1, and then we divided by 3. And so doing that became our inverse function. So if this is my original function, this is my inverse function. Okay, similar problem. I'll just pick something different. I don't know why we're angled. It's okay. So f of x equals x cubed minus 5. And again, these are invertible. We can find the inverse because these are 1-to-1. My exponents are all going to be odd. I won't have any even exponents. So x to the third power, odd. We can find our inverse. This function is 1-to-1. So again, we're going to replace f of x with y. And we're going to swap x and y. And now I want to get the y by itself. So I got to get rid of everything else. So similarly, to get rid of the negative 5, we're going to add. To get rid of the third power, remember powers and roots are inverse operations. So to get rid of the third power, we would use the third root. So this is my inverse function, that x to the third power or sorry, the cube root of x plus 5. So my inverse function is the cube root of x plus 5. So that would be the inverse of my original function.
I have a question.
Okay,
When you subtract, or when you add in the 5 to
correct.
the x, how come you don't just write 5x?
That's multiplying.
Okay, so
5 and x is 5 times x. So 5 plus x is x plus 5, or 5 plus x.
we're just being more literal here.
Oh yeah, I
in
like
a
there's,
way.
I mean, there's a difference between adding and multiplying. So the fact that I'm adding the 5 there, we're not going to write it because again, this implies multiplication, whereas this
Okay.
implies addition.
I guess we've just been doing that so much, I just didn't even think about that.
It's all right. Good question. I want to make sure we're all caught up. Okay. I'm going to do one more example, just so we have a little bit of everything to kind of go off of. So some of the other things they might throw at us. Okay, so say we have, my pen's kind of working out, the cube root of x plus, that's a 2, and then plus 3. Okay, and again, we're going to replace f of x with y. And then we're going to swap those. So x equals the cube root of y plus 2 plus 3. And again, now I want to get the y by itself. So standard equation procedures basically do the opposite here. So to get rid of a plus, we're going to minus. To get rid of the cubed root, remember roots and powers cancel each other out. So to get rid of the cubed root, we're going to use the cubed power. And then to get rid of the plus 2, we would minus 2. And remember, you can't do anything inside of that parentheses. So when it's all said and done, y is going to equal x minus 3 quantity cubed minus 2. So this would be my inverse function. That is the bulk of what this unit or this particular section is about. Usually it's about finding those inverse functions, okay? They're going to give you a function, they're going to ask you to find the inverse. They're going to give you a function, they're going to ask you to find the inverse. They can use lots of different operations, from multiplication to exponents to radicals, and you should be able to cancel out all of those different things to find those inverse functions. Just remember, the opposite of adding is to subtract. The opposite of radical is a power. Okay, the opposite of a power is a radical. The opposite of multiplying is to divide, all that same stuff. So all that same stuff you learn to solve regular equations, all still holds true. They may also ask you to show the inverse graphically. Okay, so if this is my graph of f of x, So we're going to pretend like we're going through 0, 0. Okay, that's the 0.12. So it goes through 2, 4. And then -1, -2. So again, I just labeled my points. I know that's really small, but that says -1, -2, and then 0, 0, and then 1, 2, and then 2, 4. I just labeled my points. Graphically, the inverse does the same thing. It still is going to swap your X and your Y coordinates. So instead of -1, -2, it's going to be -2, -1. Now 0 and 0, if you swap them, is still 0 and 0. Instead of 1, 2, it's going to be 2, 1. Instead of 2, 4, it would be 4, 2. So graphically, your inverse function again swaps your input for your output. It literally swaps your X and your Y coordinates. Now, sometimes they don't give you whole number pretty coordinates where it's really easy to swap. So another way to think about this is there's an invisible line here. This is actually the line Y equals X. So it's going through like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. So it's basically like on a diagonal right through there. And then a function will reflect over this line. Okay, so again, if I can kind of zoom that in, I didn't draw it super great, but you guys can hopefully kind of see from there. Like each point and its inverse point are reflected directly through this line. If you would measure the distance from here to here, and then the distance from here to here, it would be the same. It's like the distance from here to here, and then the distance from here to here are the same. So each point gets reflected over that line of Y equals X. And it does so forever. So your inverse function is reflected over this line. So you don't necessarily have to do it point by point. That's essentially what's happening. We draw another one. I'll just do a rough sketch and then I'll actually pull up Desmos and I can show you a couple others. Come on, focus. There we are. So if we had, say, a cubic function, so Y equals X cubed is pretty close to this. So again, the line Y equals X is that diagonal line right through there. Technically, this should cut over, should look more like that. Okay. So again, each point is going to reflect over that axis. So this point, I'll get out of the way. So this point here is going to reflect over that line. This point here is going to reflect over that line. This point here is going to reflect over that line. So again, you're kind of reflecting over those lines. And the inverse function would end up looking like that. I think I'm sharing my screen. Can everybody see my Desmos screen? The graph? I hope so. Okay, so this should be showing the function y equals x to the third. So that's pretty much the one that I graphed. And then the inverse function would be the cubed root of x. So it kind of inverted the colors, but you can see how those would reflect. Now, this is the line that's kind of that invisible line, that y equals x. And if you were able to measure from one to the other, okay, those points would all be equidistant. So this point would be equidistant to that point from there. In fact, if I do this right, so that'd be 1.265, 2.024. That should be 2.024. It's not letting me get directly on it, but anyway, those points are basically inverses of each other. And then anytime you cross that line, notice that's where your lines are intersecting as well. So again, this red one represents the original function. So then this blue one represents the inverse. Again, it's reflected over the line y equals x. Okay, so given an original function, if you reflect it over that line, y equals x, or if you can find any coordinates and quite literally just flip-flop them. So again, get up a little closer. So the point, come on, focus, play nice. Okay, so the point 1, 2 flips to become the point 2, 1. And again, individually, the point 2, 4 became 4, 2. So again, the inputs and the outputs just swap. Okay, like the very first example I showed you. And it's the same for this function, just there's fewer points that I can just point to. So like 0, 0, okay, and then that's 1, 1, that's -1, -1. So all of those points of intersection are the same. Then 2, 8 would be a point. So therefore, over here, 8, 2 is also going to be a point. So again, the inputs and the outputs just swap. All right, the last thing my math lab is going to ask you to do, and this is not something I'm going to put on the test, but this definitely shows up in your homework, is you can prove two functions are inverses. So if they gave you a function like this, f of x equals 5x plus 8, and now they already used the notation of the inverse of x, which is kind of funny. It's already telling you it is. But if they asked you to prove that these are inverses, okay, one way to do this is you can prove that the f of the inverse of x equals x. So basically, if you take the composite function, everything will cancel out except for the x. And you have to do that backwards as well. If you take the inverse of the f of x, everything will cancel out and equal x. So again, you got to do both. So the composition of f and its inverse will equal x, and the composition of the inverse and f will also equal x. But basically what's going to happen is you're going to plug one function into the other, and everything's going to cancel out. And then you plug the other function into the first one, and then everything is going to cancel out. So if I kind of walk through step by step exactly what it's asking you to do, you should have an idea of what it's wanting you to show on your homework. So the first thing we're going to do is that f to the negative 1 of x implies that. Okay, again, it's the f of the inverse of f of x. This is by definition of composite functions. Then what we're going to do is we're actually going to replace this f to the negative 1 of x with what it equals. Okay, we're basically going to just do substitution. Okay, f to the negative 1 of x is that x minus 8 over 5. So we're just plugging that in. So we know what the inverse of f of x is. We're just plugging that in. Then we're going to evaluate the function. So we know what f is. F is the 5x plus 8. So we're going to plug this in. So that's going to be 5 times x minus 8 over 5 plus 8. That's basically using f of x. And at this point, it's just a matter of simplifying. So if we go ahead and multiply this, so 5 times x minus 8 divided by 5.
I have a quick question.
Okay.
When you're using the 8, are you using just the 8 from both formulas? The one that's not inversed and the one that is inversed?
This x minus 8 over 5 is just this function right here. Okay. Now this 5x plus 8. So this particular 8 came from there.
Okay, that's what I thought.
Yeah, instead of x, we plugged this whole thing in to the x here. Okay, and those 5s cancel out. You divide out your common factors. So then we have x minus 8 plus 8, which negative 8 plus positive 8 is just x. If you combine like terms, then everything canceled out just like it was supposed to. Now you got to do the same thing for the other composite function as well. So that's going to look a lot of the same. So again, if we do that composite function, if we plug f of x into the f of negative 1, so basically we just replace f of x with what it is. So that's that 5x plus 8. And then we plug that whole piece into that f to the negative 1 function. So we're going to do 5x plus 8 minus 8 all over 5. Now we can't do anything with this with the parentheses there, but if we add this stuff together, so 5x plus 8 minus 8, the 8s cancel each other out, leaving me with 5x over 5. And again, if we divide out our common factor, again, we're just left with x. So there's going to be one problem on your homework where it's going to ask you to prove these two functions are inverses. You're basically going to have to walk through this and show that both of them equal x, and then you therefore have proved they are inverse functions. Again, I'm not going to put something like that on the test because to me, there's a couple of different ways you could prove it. Number one, you could just find the inverse and see if it equals this, which is what I would do. Or you could graph both and see if it's reflected over that line y equals x. So all the other stuff we just talked about. This is just another way to algebraically prove that two functions are inverses. So not something I'm going to ask you guys to do, but it does show up on your homework one time in my math lab. And you've got to show the step, and then they make you select like the reasoning Y in a drop box. Kind of a goofy thing for them to ask you to do, but it is what it is. Okay, and that's basically 5.1. Okay, that's all about inverse functions. So next, we're going to go ahead and jump into 5.2. 5.2 focuses on exponential functions. Okay, exponential functions is any function where the variable is up in the exponent. Now you can do a bunch of different things with these functions, but the fact that you have an x up here in the power. So we've done functions where we took x to a power, and that's quadratic, or if we took the third power, that'd be cubic. Okay, and we've done things where we took like the cubed root of an x or something like that. This is different though. This we're putting the actual x in the exponent. That's what makes this an exponential functions. And exponential functions are functions that get really, really big, really, really quickly. Okay, so if we show like an XY chart for this function. So if we make our exponent 0, so this is saying 3 to the 0 power. Okay, that would be 1. Anything to the 0 power is 1. 3 to the first power is 3. 3 squared is 9. 3 cubed is 27. 3 to the fourth power is 81. So you can see that these functions get really, really big, really, really quickly. So just within 4 steps, we basically went from, depending on which one you call step 1, okay, we went from 1 or from 3 to all the way up to 81. So if you're looking at the graph of an exponential function, okay, at 0, we were here at 1. Okay, at 1, we're here at 3, 2, 5, 6, 7, 8, 9. We're already at 9. By 3, we're up to 27. And then by 4, we're up to 81, which is way off of the paper. So you can see that the graph is going to do this thing. It takes off almost vertically. Okay, those exponential functions get really, really big really quickly. So and the bigger the number, the faster it's going to shoot up, and it just keeps going up and up and up and up and up and up. Okay, so regardless of what the base is, exponential functions all tend to look like this. The bigger the base number, the faster this is going to get vertical. Now, the negative side kind of flattens out. You'll see that if you were able to zoom in, you get really, really close to this 0, but you never quite get there. Okay, negative exponents just get really, 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 really small, but they never switch sides. You never get past that negative. So it's always kind of this same curve. Okay, again, I'm going to switch screens. I kind of want to go to the Desmos just because it's going to do a better job of graphing than I could ever do. So again, I really hope you guys are seeing my Desmos screen. Clear those out. So again, this is y equals 2 to the x power. And I'm going to zoom way out just so you can kind of see the bird's eye view of this graph. Okay, you can see it gets really flat horizontally and it never goes into the negative. Okay, with your standard function, okay, it gets really flat. It gets really, really close to 0. If we would zoom in over here, you would see you're very, very close, but you never quite get there. And on the other hand, it takes off almost vertically. I mean, almost straight up and down. It's not quite. And if we zoom in, you can see that it is curved. It doesn't go ever straight up and down. It just gets very vertical very quickly. And regardless of the base, that curve is going to hold pretty true. So if I get another one in here, so if I did y equals 3 to the x, okay, you can see it gets vertically a little bit faster. If we change that to y equals, say, 5 to the x, okay, it gets vertically a little bit faster. You can see the curve kind of holds true. So whenever you graph an exponential function, it's always going to have this same curve. Now, there are different things you can do to this function to shift it one way or the other. So the first thing is if we add a number outside, like a 3, okay, this plus 3 grabbed my graph and basically moved it up 3 units. So adding a number outside of the function is going to shift it up or down. If I do a -1 here, you're going to see it'll shift the graph down 1. So the red graph is my original function. This kind of purple graph is what happens if I subtract 1. It shifted it down 1. So a plus number would shift it up, and a minus number will shift it down. So that's anything going on outside of the function. Inside the function would be up here in this exponent. So this 2 to the x power. So if I do a +1 up here, okay, that actually grabbed my point and shifted it to the left. So a plus number shifts you to the left that many. So if we went +4 even, okay, that would shift my graph to the left 1, 2, 3, 4 units. Even from this point here, we would shift left 1, 2, 3, 4 units. So a plus number will shift you to the left. A minus number up in the exponent will shift you to the right that many. So this point shifts to the right 1 unit. This point shifts to the right 1 unit. In fact, the whole graph, everything shifts 1 to the right. So if we did both of those things, this -1 up here shifts me to the right 1 unit. This -1 outside of here shifts me down 1 unit. So this graph moved right 1 and down 1. If we did a plus, then we would shift left 1 and up 1. So again, the number up here shifts you right or left. Pluses go left, minuses go right. This number out here shifts you up or down. Pluses go up, minuses go down. Next, a negative in front of your function flips it over the x axis.
So a negative in front of your function flips your graph over the x-axis. So again, your x-axis is the horizontal one, the left to right. So a negative in front of your function flips it over the x-axis. A negative in the exponent flips your graph over the y-axis. So again, your y-axis is your up and down. So the negative in your exponent flips your graph over the y-axis. Okay, so again, what MyMathLab is going to ask you to do, they're going to have you graph some various functions. Now I'm going to try my best to share the screen. I want to get into MyMathLab. For those of you on Zoom, you can't see what I'm seeing right now, so hold on one second. And hopefully I'll get you into where you can see how we're going to graph. Because the good news is you don't have to graph point by point on MyMathLab, but the way they do things is kind of what I would call funky. It's all weird. Okay. All right, so into Zoom, hopefully I can share my screen where you guys can find me. All right, hopefully you guys see this. It says 5.2 exponential functions and graphs. If you can't see that, please let me know. This is in MyMathLab. I'm in the study plan, but again, I just kind of want to walk through how to graph those functions. So here's the function it wants me to graph. F of x equals 2 to the x power plus 5. So for starters, remember with MyMathLab, you got to pick the shape of the graph first. So the exponential one is this graph here. Remember, it's kind of starts flat and then it curves and goes up vertically. So this is your x squared. That's a parabola. This is your x to the third power. Okay, this is a logarithmic graph, which we'll actually talk next section. This is your exponential function. So you're going to click on it. And then you can click really anywhere in the graph and it's going to draw the function for you. So this yellow line represents the function. Now, any shifts or anything you want to do to the graph is going to be in this gray box. So for starters, this is 2 to the x power. I'm hoping you guys can see that. Okay, that's where you want to look here, where it says base. Right now we're base E. We don't want that. We want to change our base number to 2. So make sure you change your base number to whatever the base number is. So the base is whatever you're taking to the power. So 2 to the x. So my base is 2. Then any shifting you're going to do with these sliders. So the vertical shift is your up and down. The horizontal shift is your left and right. So with this graph, 2 to the x plus 5, that's going to shift vertically. We're going to go up 5. So I'm going to change this vertical shift slider to a plus 5. If we had anything going on inside of here, we would shift our horizontal. If we needed to flip anything or stretch it, we would do that with these sliders. So you shift off of the sliders, not really off of the graph. And then you tell it to check your answer and it'll check your answer for you. If I go to the next one. Oh, this is just asking me to describe what I did. So my y was 2 to the x, and I just shifted it up 5 units. Silly drop down box stuff. I want to do one more graph. I don't want to do that one. There we go. This one has both kind of shifts going on. I like this one. So this is showing 2 to the x plus 5 power minus 4. Okay. So again, you got to talk about what you're going to do. So we're going to be shifting this graph. So your base number is 2. And this graph is going to shift left because it's a plus 5. And then this minus 4 is going to shift us down 4 units. So this one we're going to have to shift in both directions. And again, Desmos or My Math Lab is not going to make you do it point by point. Again, you'll click on the graph. I'm going to zoom this in so hopefully we can see a little better. You got to choose the correct curve. There's your exponential curve. And then you adjust your shifts from the slider. So again, we've got a base of 2, not E. And then you're going to do your shifts using the slider. So you're not actually on the graph, but we're going to shift 5 units to the left. And then we're going to shift 4 units down. Okay, and again, any vertical shrinking or stretching you would do from there, check your answer. Uh-oh. Did I go, I went left 4, or what did I do? I should have went left 5. Oh, I did, yeah, I did, you're right, that said vertical shift. Ha, I'm a fool. Helps if you do read. So vertical shift down 4, horizontal shift left 5. Thank you. If I can read, I do better. Now check answer, good job. It's like you actually read the question. So whenever you do My Math Lab, that's how they're going to want you to graph. And it's going to be very kind of, they walk you through it. It's step by steps. You're not having to literally graph point by point. And remember, you can always use Desmos to check and make sure that you're doing things correctly. Okay. So that's pretty much what you're going to be doing with your exponential functions. And they can change the base value, but like I said, it doesn't change the curve a whole lot. The exponential function always is based off of that same curve. So regardless of the base, an exponential function is always going to look kind of like that. And then you can shift left, right, up, down, whatever. Now, it did show one thing. So remember it said in the base of E. So that's something we're going to need to talk about too, because we haven't talked about E yet. E is what we call a universal constant. Okay, E is a number. You're familiar with this idea if you've ever heard of pi. Pi is another one of those. Pi is a universal constant. Pi always represents the same number. Now we tend to use 3.14 as an approximation, but if you've ever hit pi button on your calculator, if you have any of those goofy kids who can recite pi to like 1,000 places or something, just as a cool YouTube trick that they learned. Okay, pi is a number. I think that's about as far as I can go. Okay, but it goes on forever and ever and ever without stopping or without repeating. Okay, you guys are familiar with pi. Okay, pi is used anytime we're dealing with something circular, round. Okay, cylinders, spheres, anything with a circular curve to it. E is also a universal constant. E does not equal one specific, well, it equals a number, but it's not a terminating number. It's a number that also goes on forever and ever and ever and ever without repeating. E is about 2.718. E is called the Euler number. E-U-H-L-E-R. That was the mathematician's name that came up with this. Okay. E is used in exponential functions. Whenever we get into compound interest, you're going to see this. This is where this came up. It works in population growth, population density. So there's a lot of time. So like pi is used in circular functions. E is used in exponential functions. Okay, so E is used throughout, usually for like population predictions. Okay, but anytime you're doing with an exponential function, that's when you're going to see E. So they're going to have you do some of these exponential graphs with a base of E. There's an E button on your calculator. Now, every calculator is different. I can't speak to all of them. But in general, okay, your calculators somewhere are going to have a log button. Usually right next to it or right above it or right below is this LN, the natural log button. And then E is always right above that. Okay, so regardless of what kind of calculator you have, as long as you have a scientific calculator, somewhere you have a log button, somewhere very close should be an LN, a natural log button, and then right above that is the E. So for my calculator, it's Shift and then LN. For some TI calculators, this is a second button. You'll hit second and LN, and in either case, okay, it should give you that E, and it's always asking to the power of. So that's how you're going to evaluate it. That also shows you that it's only used in exponential functions because you're always then using some exponent there. So if they want you to evaluate e to the third power, okay, you're literally going to use your calculator, second ln or shift ln, it should put the e there, to whatever exponent, hit equals, and then round to whatever it says to round to. My math lab usually wants 4 decimal places. That's perfectly fine by me. So whenever we do our tests, okay, rounding to 4 decimal places is a great standard. It's usually going to be accurate enough. So in this case, e to the third power would be 20.0855. So when evaluating e, kind of like whenever you use pi, we don't actually use 3.14. We use the pi button on our calculator. So same thing, when you're evaluating e, use that e button on your calculator. That's going to be the most accurate. And like I said, this is going to come up whenever we get into compound interest, which will be not next week because there's no class, but the following week. When we get into compound interest, you're going to see, and you're going to need to be able to use that E button. It does show up in my math lab a couple of different times in this, where it'll ask you to evaluate a function for that, but you're literally just punching in and hit the exponent. So same thing if it says evaluate E to the -2 power. Again, on your calculator, second ln or shift ln. Type in the power, so like e to the -2. Get your equals. About 0.1353. Nothing to it. Okay, so that takes care of exponential functions. Again, the bulk of that's going to be those graph transformations, how they slide and shift and stretch and shrink and flip. And then we'll finish with 5.3. Now, 5.3 of the sections we've covered today are going to be the most, it's going to cover the most variety of topics. 5.3 is logarithms. So this is going to be an introduction to logarithms. So it's going to hit on a couple of different ideas here. So again, we just talked about the log button on your calculator. So this is what we're going to be doing here. So we're going to be messing with logs. Log is just short for logarithm. A logarithm is the inverse of those exponential functions. So that kind of ties together what we started with. 5.1 was your inverse functions. You learned what an inverse was. 5.2 was exponentials. 5.3 is the inverse of the exponential function. That has a name. It's called the logarithm. So your logs are the inverse of the exponential function. So the first thing we got to understand is how to use logs. So as an exponential function, okay, 2 to the third power is 8. Remember, power is just say to multiply something that many times. So this is saying 2 times 2 times 2 is 8. Okay, we can rewrite this as a log. Logs are written like so. Now I'm going to kind of go elementary here on you, okay? If you have little kids in elementary, if you can remember elementary school and you learned how to write cursive. Okay, you had these little lines are kept, that way all your letters were the same size. All right, so we're going to go elementary here. So that's where your log is. Okay, the 8 and the 3 are on the same level and are the same size as the log. This is going to be really important because if you miswrite this, it actually means something very different. So the way you notate it, the way you write it is extremely important because what you mean to be saying and what you are saying might not be the same thing. Got a joke. I went to Spain one time and I was using what I thought was Spanish, but it was actually like it's a Mexican dialect. It didn't mean the same thing. So I thought I knew what I was saying. I didn't know what I was saying. So anyway, this is the same thing. And then the 2 here is a sub number. So it's below and slightly smaller. So this is how we should be writing logs. Usually I run into people with really nice handwriting or the ones that mess this up. They'll mean this, but what they write is this. And that is not at all even remotely close to correct because we're going to talk about what happens when you don't see a sub number. It has a meaning. Okay, and right now this 2 is on the same level as the log, so it's no longer the base number. So where and how you write it is extremely important. Your sub number should be smaller and below than whatever you're taking the log of, and what it equals should be on the same line and about the same size as your logs. So when you write it, make sure you're writing it correctly. Anyway, next, kind of how these relate. So the 2, your base number, so whatever you're taking to the power of, okay, becomes that sub number. So whatever your base is, doesn't matter what number it is here. If we were doing 4 to the 5th power or e to the 2nd power, okay, this number becomes your sub number. The answer to your exponential function is now what you're taking the log of. And then your exponent is essentially what the log is equaling. So again, remember your inverse function swapped inputs and outputs. So for this one, your input was 3 and your output was 8. For the log, your input is 8, so now your output is 3. That's that inverse. It flip-flops your input and your output. So the first couple of things are just simply asking you to rewrite an exponent. That's a 2. As a log. So 5 to the 2nd power equals 25. Could be rewritten as log sub 5 of 25 equals 2. So again, your base becomes your sub number. Your exponent becomes your output. Your answer becomes your input. That also works in the opposite direction because you're going to have to convert from a logarithmic to an exponential. So again, the sub number becomes your base. Whatever the log equals is your exponent. And then whatever you're taking the log of is now your answer. So log sub 10 of 1 equals 0 can be rewritten as 10 to the 0 power equals 1. So that's how exponential functions and logs relate to each other. So this is logarithmic. This is exponential. They mean the same thing. It's just written in 2 different ways. And if you graph them, they are inverses of each other. So again, input, output, input, output. Now, also, if you have a log with what they say no apparent base, if they don't write a sub number, this is one of those times in math where it's there, it's just implied. They don't always write it down. In math, that's usually a 1. However, with logs, that's not the case. Okay, if there's no apparent base, if they don't give you a sub number, it's automatically a 10. Wow, that's really crappy handwriting. So again, a log with no sub number is a 10. So when there's no base number, it's automatically a 10. Which is what I tried to write there with really crappy handwriting. Okay, so if they tell you to evaluate a log, for example, if you're just told to evaluate the log of 5, what's being asked is 10 to what power equals 5. Now, this is going to be some kind of decimal because 10 to the 0 power is 1, 10 to the first power is 10, so it's going to be somewhere in between there. And that's where that log button on your calculator comes into play. So get my calculator up here where you can kind of see it. Okay, if I want to take the log of 5, I can hit log of 5. And that's going to be about that 0.69897. So if we round that to 4 decimal places, okay, the 7 makes the 9 round up, so it's going to be 0.6990 roughly. Okay, so if they ask you to evaluate a log, you're going to use your calculator. But this is what it's asking you to find. That's what this number represents. Okay, so the log of 5, come on, focus. There we go. Okay, the log of 5 is asking 10 to what power equals 5. And then we can use our calculator to approximate that. And again, as long as you go to 4 decimal places, that's going to be accurate enough. It's not exact, but it's close enough. Now, another thing they may ask you to evaluate is that ln. And again, ln is a button on your calculator. The ln is for base E. So with ln, they'll never write this, but it's implied that this is base E. So again, what it's asking is E to what power is going to equal 5. So that's what it's asking. So when you type into your calculator, okay, so again, calculator, if I hit that ln button, so wherever your log button is, right next to it should be the ln button. So if I hit that ln of 5 and hit equals, I get about 1.6094. Okay, again, that's answering the question, E to what power is going to equal 5. So log with no apparent base. So if there's no number here, it's a 10. If we need to approximate it, we're going to use our calculator. Same thing, if you have the natural log, that ln means natural log, it's base E. And again, we're going to use our calculator. This is just what it's asking. So that's what this number represents. That's going to be the first few things. So you need to be able to convert back and forth between logarithmic and exponential functions. You need to be able to evaluate a log with no apparent base and a natural log. Now, they are going to have you evaluate a log with an apparent base. And this is actually what logs were invented for. Without the use of logs, it was a bunch of guess and check. So we'll start with a problem we can kind of guess and check here. So if we said the log sub 2 of 8, this is a problem we've already done. So again, what this is asking is 2 to what power is 8? Well, you'd have to kind of guess and check. Well, 2 to the 0 is 1, 2 to the first power is 2, 2 squared is 4, 2 cubed is 8. Aha, got it. X is 3. So this log sub 2 of 8 is 3. Now, as long as you get pretty little whole number answers, that works out really, really good. If we want to evaluate a problem like so, the log sub 6 of 7, again, what this is asking is 6 to what power is 7? Uh-oh. Well, 6 to the 0 power is 1. 6 to the first power is 6. 6 squared is 36. It's none of those. So it's got to fall somewhere in between here. So it's got to fall somewhere between 1 and 2. And at that point, you're having to do a bunch of guess and check, and you got to try decimals. And if you got to go to 4 decimal places, oh dear goodness. Okay, that's no fun, right? So we have a method for this. So with this, we're going to use what's called the change of base formula. And again, we're going to get to use our calculator. Thank you, calculator. Back in the day, my dad was an engineer. He took these classes in Rolla before the days of calculators. He did this with a slide rule. Oh, poor fool. Okay. He was born too early. Calculators do so much of our work for us. It's so nice. All right. So change of base formula. To evaluate this, we're going to take the log of 7 divided by the log of 6. So again, this is using that button on your calculator. So handy dandy calculator. Come on, focus, got it. Okay, so we'll do the log of 7 divided by the log of 6, making sure we close our parentheses. Hit equals, and it's about 1.0860, which again, we knew it was going to be somewhere between 1 and 2. Just without having to do all the trial and error, we can get there. Now, some of you are even luckier than that. You don't need the change of base formula. If you've got a calculator that's sophisticated, for example, if you have the calculator I told you to get, that FX 115 ES Plus, okay, you'll see up here you've got a log button with these boxes. This calculator actually allows you to change the base on the calculator itself. So if I hit that button, okay, you'll see I got some boxes here. So I got a little box sub number and I got a box here. It's kind of dark, it's tough to see. But I can type in my 6 and then my 7 and then just hit equals and I get the exact same answer. So that 1.0860. So if your calculator is sophisticated enough, you don't need to use the change of base formula. You can just type in a log with a different base. Now, if you don't have a calculator that's sophisticated, it's not like I'm asking you to, invent the wheel or anything here. It's just log of 1 divided by the log of the other. But if you have the right calculator, you can shortcut it. Just type in the exact problem you started with. So you should be able to evaluate a basic logarithm with no base. You should be able to evaluate a natural log. And then you should be able to evaluate a log with a different base number. So log sub 6 or like log sub 2 of 8. So again, if we were doing this problem, we would do the log of 8 divided by the log of 2. Again, handy dandy calculator, log 8. Oh, it's so dark you can't see that. So log of 8, close my parentheses, divided by log of 2, close my parentheses, equals 3. Just like it was supposed to, just like we said, it's 3. So they're going to give you a bunch of different logs to evaluate for. All right, the last thing we're going to talk about is just like with the exponential functions, we're going to talk about the graphs of log functions. Again, remember, your exponential functions look like so. So a logarithmic function is going to look like that. Actually, should look like that. So just like your exponential function doesn't cross the zero, your log gets really close to the vertical axis, but it's never going to cross it. And then it's going to go up, and then it's going to get really flat. Because my graphing skills suck, again, we're going to go back to Desmos. So see if I can share my screen. Where did my Desmos go? My Desmos ran away. All right, hold on. There we are. Okay. Share screen. I want Desmos. All right, hopefully everybody can see my Desmos screen. So again, these were your exponential functions that we were looking at. Now we're going to do logarithmic functions. All right. I can put that over there for now. All right, so again, a logarithmic function gets vertical at the y-axis, cuts across your x, and then takes off almost horizontally. It's still going up, it's just getting really flat. We zoom this in, you can see the curve a little better. But that's going to be your typical logarithmic function. And it actually shifts the exact same as those exponential functions. So if I add some number outside of the function, okay, so like this +2 outside is going to grab my graph and it's going to shift it up 2. It looks like it's going up 4, but it's because the scale of the graph is off. So if we zoom that out, then you can see that it goes up 2 units. Okay, so each point gets grabbed and shifted up 2. And same thing, if I subtract something outside of the function, that's going to take the whole thing and shift it down 2 units. Now, if I draw some parentheses here, so if I'm going inside of the function, again, a plus is going to shift it to the left. A minus would actually shift it to the right. So again, anything being done outside of the function, like this +3, shifts up. Anything in parentheses here inside of the function shifts it left and right, and it moves backwards. So again, the minuses move right, pluses move left. And then negatives are still going to make things flip. So if I put a negative in front of the log, that shifts it, reflects it over the x-axis. So it flips it vertically. If I put that negative inside and make my x negative here, that flips it over the y-axis. So that flips the whole thing horizontally. So again, when you go into My Math Lab, you're going to do the exact same thing. You're going to click on the graph. You need to make sure you're grabbing the right curve, and then you're going to adjust your shifts using those sliders. It plays just like the exponential function. So I'm not going to hold your hands and walk you through all of those. You guys are capable. And that pretty much takes care of that. So I probably mathed your brains out. We've done 3 sections. Remember, no class next week because of the college development or whatever. And then we will cover another 3 sections the following week. So no seated class time, no Zoom lessons. next week. The next week we'll cover lessons 5.4, 5.5, and 5.6. So I'm here for a while. I'll answer any questions you have. But basically, if you're good to go, then I'm going to trust you to get your stuff done. Make sure you're getting your stuff done in my math lab. Covering those 3 sections, you're going to have those 3 homeworks to do. Each one, I think, has like 10 questions, give or take, thereabout. So make sure you're going through and doing your stuff. You're not going to have a whole lot of time. We get through this unit really quickly. And then that 3rd exam happens. Then we pretty much do the same thing. And then that 4th exam. So we're over halfway. Double check. You should have got your midterms over break. So you should have got those. Anyway, make sure you're getting the grades you want. Turn in your stuff. Do your thing. If you have any questions, ask them. I'm here. Otherwise, I'll see you in 2 weeks.
You have a great night.
All right. See you, Joe.
And then for my exam for the week of the 12th, I'll
Yes.
do it on the 9th. So just email me and let me know when you're able to set it up and everything.
Okay. Yep. I can actually have it in relatively early. So if you want to try and take it before those sections are happening, I can make that happen. You tell me, so what is a better day? Like, when would you like to test? What's your best time? do you think?
Honestly, the 9th would be fine for me because that's like the latest date I could do before I leave. So they'll give me some time to look over all of those slides and
Okay. And
prepare
that's
for
that
that.
Friday. That's that Friday, right?
Yes.
Okay. I will definitely have it ready by then. I'll probably go ahead and submit it that Thursday.
Uh-huh.
I'll have it done, but you can do it that Friday then.
Okay. Thank you.
No problem.
Mr. Dale,
Yes.
for my grade for 4.4, on my lab, it says 100%, but in the grade book, it says 10 out of 100.
Okay. I'll double check that. Thank you. This is Mackenzie,
Okay.
right? Is that Mackenzie?
Yes,
Okay. Got it. Yeah. I'll double check it.
okay, thank you.
No problem.